Hello everyone, in this theoretical tutorial number 56 we will review the bad zero analysis and the method to solve it by adding a resistor R in series with a capacitor. We will explain the amplitude and phase modification by doing the sum of vector for the angular frequency omega 0 and twice omega 0. The common source amplifier using an NMOS transistor is shown with an ideal current source, meaning infinite output impedance. The small signal analysis diagram is created with capacitor C representing the gate-drain capacitance and the drain current GMVI with the transconductance of the NMOS transistor GM. Of course, we can perform the vector sum Vout plus Vc equal Vin. Thus, Vc equal Vin minus Vout is the voltage across the capacitor Gm times Vi over Jc omega. After arrangement, we obtain the gain Vout over Vin in the yellow rectangle. It's now interesting to find the phase between Vin and Vc. The voltage across the capacitor is Vc equal Zc times I, or I over Jc omega. But since I equal Gm Vin, we get Gm Vin over Jc omega. Now let's multiply the numerator and denominator by J, and we will get Gmvi over J square C omega. Before continuing, I'd like to open a paragraph to discuss the mathematical operation of vector multiplication. The bold red star represents specific vector multiplication. To multiply a vector, we multiply its modulus and add its angle. Since vector G has a modulus of 1 and 90-degree phase, the result is -1 on the real number axis. Thus, the vector Vc equal minus J Gmvi over C omega is proportional to Vin, and its phase at 90 degrees is directed to the negative direction as shown in the diagram. On the right, I have represented the impedance of the inductor ZL, the resistor R, and the impedance of the capacitor Zc in the complex plane. Now that we know the phase of Vc versus Vi, we can plot the vector diagram on the complex plane. We first place the vector Vin on the real axis for reference. We also know that Vc is on the negative imaginary axis, but since the two tips of vector Vin and Vc are touching, we need to move the vector Vc. We can now plot the vector Vout to get the phase and gain of Vout versus Vin. The gain of the common source amplifier with infinite load resistance is shown in the yellow box. When omega is small, Gm over C omega is greater than 1, therefore the gain can be written as minus Gm over C omega, and we can plot the low frequency gain asymptote. This asymptote cuts the horizontal asymptote representing the gain 1 or 0 dB when omega 0 equal Gm over C. The voltage Vc across capacitor C is Gmvi over Jc omega. If we set Vin equal 1, the asymptote represents the voltage Vc. So when the asymptote crosses 0 dB, it means that Vc equal 1. If we calculate the sum of the vector starting with Vin equal 1 horizontally, we need to place the vector Vc equal 1 at 90 degrees as shown on the previous slide. We can then plot the vector V out to find the gain of 3 dB, 1.4, and the phase of 45 degrees when omega 0 equal Gm over C. See the red dot. The 6 dB intersects the asymptote at omega equal omega 0 over 2, means Gm over 2C. At this point, Vc equal 2, we can first place Vc and calculate the sum of the vector V out plus Vc equal V in, plotting the vector V out to obtain a phase of 63 degrees and an amplitude of 7 dB or 2.23, as indicated by the green dot. If the asymptote continues to cut off the minus 6 dB at omega equal 2 omega 0, means 2 Gm over C, we can plot Vi equal 1 and vector Vc equal 1 over 2. Then plot vector V out to get the phase of 26.5 degrees and an amplitude V out of 1 dB, means 1.12. As omega approaches infinity, Gm over C omega is very small compared to 1. As Vc approaches 0, V out over V in equal 1. After this 3-point calculation, we can graphically represent the gain and phase of the equation V out over V in equal 1 minus Gm over C omega. If we plot in bold the higher of the two asymptotes between minus Gm over C omega and 0 dB, we see that the gain is 3 dB relative to the crossover point at omega 0 equal Gm over C, but for omega equal 2 omega 0 and omega equal omega 0 over 2, the gain is just 1 dB relative to both asymptotes. Here are the main characteristics of the bad zero. The gain is limited to 1, but the phase goes from 90 to 0 degrees. This bad zero is due to the capacitor C between the input and output. So at high frequency, the capacitor is shorted with Vc equals 0, then V in equal V out with the same phase, which means that the phase V out over V in is 0 and the gain is 1. To compensate for the bad zero, we place a resistor in series with capacitor C. Of course, if R equals 0, we have the bad zero characteristic. As a reminder, we use the vector construction for R equals 0. The voltage across R is R times I. Since I equal Gm V in, VR equal R Gm V in. Now, if R equal 1 over Gm, we define the dotted curve for R equals 0 as a reminder. VR equal V in, and VR will always be equal to V in and with the same zero phase. Since V in equal V out plus VR plus Vc, we can put the vector VR into the new vector construction and find the vector V out, which has the same magnitude of V in, means a gain of 1, and a phase of 90 degrees. We now perform the same vector construction for an angular frequency of 2 Gm over C. At this angular frequency, we have already seen that Vc equals 0.5 and that V out always has a phase of 90 degrees with an amplitude of 0.5. With this specific R value equal to 1 over Gm, we suppress the zero, which means that the amplitude continues to decrease with frequency and the phase is always as 90 degrees, represented by the graph in bold red. The mathematical calculation can also be performed by starting with the sum of the vector and replacing VR and VC with their respective expressions. We can then write the equation of Vout as a function of Vin and replace R with 1 over Gm to obtain the gain equation Vout over Vin equal to minus Gm over Jc omega. To compensate for the bad zero, we place a resistor in series with capacitor C. Of course, if R equals 0, we have the bad zero characteristics. As a reminder, we use vector construction for R equals 0. In this slide, we will replace R with the value 2 over Gm, and using vector construction, we will better understand how to maintain a zero with a phase at 180 degrees instead of 0. The voltage across R is R times I. Since I equal Gm Vin, VR equal R times Gm Vin. Now, if R equal 2 over Gm, we define the dotted curve for R equals 0 as a reminder. VR equal 2 Vin, and VR will always have the same phase 0. Since Vin equal Vout plus VR plus Vc, we can insert the vector VR into the new vector construction twice as long as Vin and find the vector Vout, which is equal to the square of 2, meaning a gain of square root of 2 and a phase of 135 degrees. Note that the gain Vout over Vin has the same 3 dB gain as with R equals 0, but a phase of 135 degrees instead of 45 degrees. We now perform the same vector construction for an angular frequency of 2 Gm over C, which means 2 omega 0. At this angular frequency, we have already seen that Vc equal 0.5. As Vc decreases, the vector Vout must increase the angle to 153 degrees, but still with the same amplitude as with R equals 0. If the angular frequency omega tends to infinity, Gm over C omega will be really small compared to 1, so Vc will tend to 0. Therefore, the vector construction shows that Vout will tend to the phase of 180 degrees, which means that the gain Vout over Vin will tend to minus 1. With this specific R value equal to 2 over Gm, we keep the 0 at the angular frequency of omega 0, which means that the minimum gain is 1, but the phase changes from 90 to 180 degrees, represented by the graph in the bold red. The mathematical calculation can also be performed by starting with the sum of the vector and replacing VR and Vc with their respective expressions. We can then write the equation of Vout as a function of Vin and replace R with 2 over Gm to obtain the gain equation Vout over Vin equal to minus 1 minus Gm over Jc omega. I want to thank you for your attention. On my next heuristic car tutorial number 57, after reviewing the zero, we will be more focused on the pole with always looking the vector construction. So, see you soon and stay tuned.